This video is going to go through a couple of quick examples of how to solve simple trig equations. If you need the lengthier, if I'm going too fast in this video, make sure you check my channel for the longer explanation video. But here we go. Let's say I have secant theta equals 2. I like dealing with the original trig functions, the OGs, so I'm going to change secant into cosine theta, which is just we do the reciprocal of 2 over 1, which is 1 over 2. So first thing I need to identify is that cosine is positive. So I need to know where the cosine angles will be positive, or where theta would be positive. Alright, so if it's positive, again I like writing this, C-A-S-T, or all students take calculus, whatever device you want to use there. So, and again, A stands for everything's positive in quadrant 1. S is for sine, meaning sine is positive in quadrant 2. T is tangent, and tangent is positive in quadrant 3. And C is cosine, and cosine is positive in quadrant 4. So if cosine is positive, that means it has to be here, because everything's positive there. And C is positive, right? Because cosine is positive in the 4th quadrant. So my angle cannot be in those 2 quadrants. But that leaves me with 2 places that cosine's angle could work. Alright, so if I'll make my triangle here, and use the information given, cosine is adjacent over hypotenuse. And looking at my information here, I can see that the missing side, if I know my special right triangles, is a radical 3. And if it's radical 3, then that means it's a 30, 60, 90. But the real question is, what's the reference angle? Meaning the angle closest to the origin. Again, it's opposite radical 3, meaning my reference angle is going to be 60 degrees. Or pi over 2, correct? Or pi over 3. It's going to be pi over 3. So, now the question is, so if it's in the first quadrant, pi over 3, starting here at the positive x-axis, obviously theta is going to be pi over 3. And if I were to go all the way around, 2 pi over 3 would be here, 3 pi over 3 is on the axis, 4 pi over 3 is there, 5 pi over 3 is where this happens. So 5 pi over 3. And there we go. And again, I didn't mention this, but always assume, even if I don't write it, that 0 is less than theta, which is less than 2 pi. Meaning, we only want the angles within 0 and 2 pi, or from 0 to 360. Because, right, if I keep going in the circle, wouldn't I keep getting the same answers? Yes. So, rather than redundantly keep going on, we just say, oh, from 0 to 2 pi. And those are the 2 angles where cosine is equal to 1/2. Alright, let's do another example here. Let's do cotangent of theta equals 1. Like I said, I like dealing with the originals, so we'll do tangent, and again it's 1 over 1, but it still remains of 1 over 1. Alright, so first thing I recognize, tangent is positive. Which quadrant is tangent positive in? Tangent would be positive in the all and in the tangent, right? So it can't be here in 2, or it can't be in quadrant 4. Alright, let's draw my triangle. And tangent is opposite over adjacent, or y over x. So 1, 1, and 1, 1. Now you might be saying, well wait, I thought the ones had to be negative here in the 3rd quadrant. They do, but remember, negative 1 over negative 1 makes positive 1. So, just be aware of that. Alright, so, and if I'm savvy with my special right triangles, I know that, I put the 1 in the wrong spot there, sorry. This is going to be 45, 45, 90, so that's radical 2, and this is radical 2. So my reference angle is going to be 45, but in radians it's pi over 4. Alright, so now I need to know how far in the rotation my pi over 4 reference angles are. Well, obviously, starting at the positive x-axis, I'll do it here in orange. So I've started on the positive x-axis, the first stop there is pi over 4. But what about the angle in the 3rd quadrant? Again, 2 pi over 4 would be there, 3 pi over 4 is here, 4 pi over 4 is here, 5 pi over 4 is right there. So 5 pi over 4. So those are the two answers for cotangent equals 1. All right, let's do one more example. Let's go ahead and do, let's do something nice. Sine of theta equals negative radical 2 over 2. Negative radical 2 over 2. All right, so if I have this situation, again, we have to identify where sine is negative. So I'll do my little chart here. So sine is negative. So it can't be here because everything's positive, and it can't be here because sine is positive. So the only two places are where sine is negative. And remember, sine is the y value, and it has to be negative, meaning below the x-axis. There we go. All right, let's go ahead and graph my angles here. So it looks something like that, something like that. All right, so sine is negative radical 2 over 2. Now I'm going to, okay, we'll do it this way first. So sine is y, so negative radical 2 over 2. And then over here as well, so negative radical 2 over 2. All right, so now we have to identify what the angle is here, but this isn't necessarily a specific right triangle, is it? So I'd need Pythagorean theorem to prove it's a right triangle, wouldn't I? Yes, I would. So if I do Pythagorean theorem, it's going to be negative radical 2 squared plus b squared. We'll say x squared. We'll be a little more fancy. Plus x squared equals 2 squared. So if I square the radical, it goes away, so I'm just left with 2 plus x squared equals 2 squared is 4. Subtract the 2. X squared equals 2, square root, x equals radical 2. And then hopefully you look at that and say, hey, wait a second. If both the legs are the same, then that must mean this is a special right triangle, correct? If both legs are the same, then they have to be, the other angles have to also match. So it's 45-degree reference angle, or in radians, it'd be pi over 4. Okay, so they're both pi over 4. But now the real question is, how far in the rotation is pi over 4? So starting here, again, this would be 1 pi over 4, this is 2 pi over 4, 3 pi over 4, 4 pi over 4. This is 5 pi over 4, so theta is 5 pi over 4. And then this would be 6, and 7 pi over 4 is the last one. Okay? So that is how we do very simple, basic trig equations. There's a lot of more complications to it, but that's where we're going to start tonight.